with method of management. So today we will be discussing a number of topics. The first topic that I would like to discuss with you is three natural variations. As we discussed before, free and natural variations or free vibration when the system is disturbed, the force of excitation is applied, but during the vibration, there is no force of excitation. And the system is vibrating by its own. It is vibrating in the absence of the force of excitation. So such type of vibration is known as free vibration or natural vibration. Let's say that we have a system and we want to model it. And we would be doing lump parameter modeling. So let's say that we are modeling that system as 1 degree of freedom. So it would have one mass. So let's say this is the whole mass. We are taking all of the mass of the system as lump mass. In the real system, the mass will be continuously distributed, but we are taking at one side. So this is lump mass. Similarly, the stiffness, the elasticity in the system is actually, in reality, would be distributed or continuous. However, we are taking all of the elasticity in this spring. So the elasticity is lumped, and also the mass is taken as lump parameter. And the damping, normally we discussed last time that the damping represents the energy losses which occur during the vibration of the system in the form of friction and other resistances. But let's assume that for the sake of simplicity, we are ignoring the damping in the system, meaning that the energy losses in the system. The system is the conservative system. The energy is neither going or neither coming out into the system. So let's say we have this mass. It is attached to this spring. One end of the spring is fixed, whereas the other end of the spring is connected to this mass. And we initially, let's say I'm pulling this mass to, let's say, this much distance, and then I am releasing the mass. So this disturbance is actually pulling here. And then when I release the mass, so what would happen? This mass would start vibration about a mean position. So let's say this is a mean position, so it would start vibration about this mean position. So the to and fro motion, which repeats itself after an equal interval of time, is vibration. And this mass is actually vibrating at its own in the absence of the disturbance, which was actually the pulling of this mass. So this kind of vibration would be free or natural vibration. K is the stiffness of this thing. Stiffness is actually normally defined for the material, and it is defined as the mass, as the force which is required to produce unit deformation inside the material. So the force which is required to produce unit deformation inside the material. Let's say we applied a force on the material, and the material is elastic, it is not rigid. What would happen? Deformation would occur inside the material. And the force that is required to produce unit deformation, this K would be equal to force that is required to produce unit deformation or displacement inside the material. So F X. Let's say F is the force which we are applying on the material, and X is the deformation which is actually happening inside the material. So according to the definition, stiffness K would be equal to force divided by deformation. So stiffness is F by K. Or the spring force, the force which is in this spring because of this vibration, it would be F is equal to, from that above equation, from the stiffness equation, it would be F is equal to K. Here K is the spring constant, we call it the spring constant or stiffness of the spring. So we have uh, a system, undamped system, and we are vibrating that system, and it is under free vibration. The system is under free vibration, and it would be vibrating at the natural frequency. The frequency of the system, natural frequency, or undamped natural frequency. Undamped natural frequency because we are not considering the damping in the system. Such type of system is known as undamped vibratory system, and its natural frequency would be known as undamped natural frequency. The circular frequency, of the system, the circular frequency of the system is denoted by omega n, and it is equal to under the root K by n. K is the stiffness of the spring constant, and m is the mass of the system. So this is the mathematical model for the undamped natural frequency or natural frequency of the system. When the system is vibrating, when it is moving to and fro, and it is repeating itself, so we have a periodic motion. Most probably sinusoidal motion or harmonic motion. Simple harmonic motion. You may have studied simple harmonic motion. Simple harmonic motion is when acceleration is directly proportional to the displacement with the negative sign, and that negative sign means that acceleration is always directed towards mean position. So mathematically, simple harmonic motion means that acceleration is directly proportional to displacement x, displacement of the mass, and there is negative. So acceleration is directly proportional to displacement, and the negative sign means that the acceleration is always directed to the mean position. So this is actually the definition of the simple harmonic motion. So normally, in most of cases, we would assume such type of vibration as simple harmonic motion. And if we want to plot simple harmonic motion is sinusoidal motion. So if we plot a sinusoidal motion, then the plot would be like this. This would be the plot of the sinusoidal motion or sinusoidal vibration. X of t is the displacement of this mass. X of t is the displacement of this mass with respect to time. So this is the time response of this system. And as you see that the displacement reaches the maximum, then it would decrease or fall down, and it would come to the mean position, which is the mean position of the displacement of the system, and then it would move in the opposite direction, and again it would reach to the extreme position, and then again it would move towards the mean position, it would reach the mean position, and then it would move towards the other extreme position. So we would have a mean position. Let's say it is the mean position about which this mass is vibrating. This mass would move in that direction. It would reach the extreme position. So here we would have the, let's say, the positive extreme position, and then from there it would stop and it would return back to its towards its mean position because of the spring. The spring would be pulling the mass, so it would be retracting back towards the mean position. So it would reach the mean position, and then the inertia would further move its mass towards the other extreme position. So here we would have the other extreme position. When the mass reaches here, again it would become at rest or stationary, and again from there, this spring, as the spring would have been compressed, so it would push the mass back towards the mean position. So in such a manner, this mass would be vibrating or moving above this mean position. It will reach one extreme position and then the other extreme position. And this motion is plotted here. This is the time response of the system. X is the displacement of the system, and generally in vibration we call it response of the system. And as you hear, this is the time plot. Here, along the horizontal axis, we have time, and along the vertical axis, we have the displacement. So this is the time response of the system. That what is happening to the displacement with respect to time. And you can see here, this is the maximum displacement. The maximum displacement is known as amplitude. It is known as amplitude, and the time taken to complete one cycle, this is the time taken to complete one cycle, is the time period. Is the time period, and it is actually equal to 2 pi by omega n, where omega n is the circular natural frequency of the system. So we would have a sinusoidal motion. We would have a crest, trough, amplitude, wavelength, all those terminologies which are actually associated with the wave. Omega n is the circular natural frequency of the system. Its unit is radians per second. And the relationship between the frequency and circular natural frequency is that is actually f is equal to f, f is equal to 1 over 2 pi omega n. So omega n is equal to 2 pi fn. That is actually, you may have heard that fn is actually equal to 2 pi omega and subscript n. The subscript n stands for natural vibration or natural frequency. Omega n is the natural frequency of the system. This n subscript n stands for the natural. The unit of this f subscript n is hertz. Its unit is hertz. Its unit is hertz. It is cycles per second. And unit of this omega is actually radians per second. The circular natural frequency, radians per. You have to keep this in your mind. So, okay, so let's. So mathematically, this is actually the mathematical model for the natural frequency of undamped system which is moving and its vibration is free vibration or natural vibration. This is called lump parameter model, or it is also known as string mass system. This is the simplest model for a vibratory system. Simplest model for a vibratory system. It would have one natural frequency. And you could easily see that it is 1 degree of freedom system. This is 1 degree of freedom system. So simply, if you want to model the real system, continuous system, and if you want to find out the fundamental frequency, that is the first frequency of the system, then actually just model it as a first degree of freedom system, ignore the damping, and then find the undamped natural frequency with this mathematical model. For this mathematical model, what you would need? You would need the thickness term and you would need the mass. If you know these two terms, then very simply you could compute the natural frequency of the system. So from where we got this mathematical model? Because omega n is equal to under the root k bar n. So on the coming slide, we would be discussing that how that model is obtained for a vibratory system. So let's say we have a system, single degree of freedom system, and it is under natural or free vibration. Then the equation of motion of the system should be written as mx double dot plus kx is equal to 0. The derivation of this equation would be coming in the next slide, so you have to wait for that. But you could see the actually the terms in the equation. So x is what? X is the displacement. K is the thickness of the string constant. Kx is the spring force. It is the spring force. X double dot. X is displacement. If we differentiate this with respect to time, if we take derivative of that, we would get velocity at which this mass is vibrating. If we take another derivative with respect to time, then it would be x double dot, and that x double dot would be the acceleration of this mass during the vibration. And x double dot is actually the inertia force. This is the inertia force. So this is the inertia force plus spring force. The sum of these two must always be equal to 0 during this vibration. So this mathematical or differential equation is actually representing the motion of the system during the whole of the vibration at all instances. So this is the equation of motion of the system, and vibration is happening, and the vibration is simple harmonic motion, it is a periodic motion, and a sinusoidal motion. So if we have a sinusoidal motion like this, if we have sinusoidal motion, then mathematically we could write that sinusoidal motion as x of t is equal to a sine omega nt. The system is vibrating, and it is vibrating at the natural frequency. So the frequency would be omega n. The subset n stands for the natural frequency. And it is sinusoidal motion, so sine omega nt. Omega nt is a frequency. And capital A is amplitude. It is the amplitude. So if we have a sinusoidal plot, mathematically we could write that in this mathematical form. X of t is equal to a sine omega nt. This would be the equation for this displacement. So displacement is actually called response of the system. So this would be the response of the system in mathematics. Or mathematically, This is the response. So if this is the response of the system, then it must satisfy the equation of motion, this differential equation. So here you could see that we have x double dot. So in order to have x is already there, and in order to find x double dot, we have to take derivative of x with respect to time. So we would have x naught is equal to a constant, it is the amplitude of the vibration, and then we have sine omega nt. Sine omega nt would be cos omega nt, and then it would we have to derivate this with respect to time. When we derivate this with respect to time, we would have omega n. So x dot is equal to a omega n cos omega nt. And if we derivate this again with respect to time, then we would have x double dot. A is constant, omega n would be there, and then cos omega nt is minus sine omega nt, and again we would derivate this with respect to time, and 1 omega n would again the negative sign is here, and 1 omega n would again come out of that, so we would have omega n squared. So x double dot is equal to minus a omega n squared sine omega nt. So putting for x in this equation and putting to x dot in this equation. After putting in that, we would have this equation, and in this equation you could see that we have minus m a omega n square sine omega nt plus k sine omega n is equal to 0. So we could take k sine omega nt as common. So if we take that common, so what we would have I'm taking k sine omega and t is common. Then inside the bracket we will have minus m omega n square plus k is equal to 0. So we have a sine omega n t and minus omega n square plus k is equal to 0. What does it mean? It means that either this quantity a sine omega n t is equal to 0 or minus m omega n square plus k is equal to 0 at all times during vibration. At all times during vibration. So now mathematics is saying to explain to us that either this quantity is 0 or this quantity is 0 during the vibration at all instances. For time 0 to infinity, either this is equal to 0 or this is equal to 0 or both is equal to 0. There could be all these three possibilities. Now we have to compare this result with the physics of the system. The reality. A sine omega nt is what? A sine omega nt is the displacement. It is the displacement. And we know that displacement is 0 at the mean position. It is 0 at the mean position, but it is maximum at the extreme position during vibration. So displacement cannot become 0 at all times during the vibration. A sine omega nt cannot be 0 during all of the vibrations. From 0 to, when time is equal to from 0 to t. Displacement will be only 0 at the mean position. All other instances, either in this direction or in this direction, we would have displacement during the vibration. It would have value. So our physics is saying that a sine omega nt would be not equal to 0 at all times during the vibration. What does that mean if it is not equal to 0 at all times, at all instances during the vibration? What does it mean? It means that the quantity which is inside the bracket, that is minus m omega n square plus k, it must be equal to 0, meaning that this quantity is equal to 0 at all times during the vibration, during all of the vibrations. So minus m omega n whole square plus k is actually equal to 0, is equal to 0 when t, that is time tends to from 0 to infinity. At all times during vibration, as long as the system is vibrating, this quantity must always be equal to 0. This is actually the physics of the system. This is the reality of this vibratory system. And from this equation, we could, I could take this quantity on the other side of the equation, and we would have, or I could take this quantity on the other side of the equation. So it would become minus k. This minus would cancel with this minus, and we would have omega n square is equal to k by n. K by and taking square root on both sides, omega n is equal to under the root k by n. So, using mathematics and the reality, the physics of the system, we finally come to know that the circular natural frequency omega n is actually equal to k by n. This is a mathematical model by which we could find out the fundamental frequency of the system. Fundamental is actually the lowest frequency of the system. Real systems are continuous systems. They are distributed. They would have infinite number of degrees of freedom. Infinite number of degrees of freedom means they would have infinite number of natural frequencies. But the system would have the lowest frequency, and that lowest frequency would be 1. We call it the fundamental frequency. Single degree of freedom system would have 1 frequency. 2 degree of freedom system would have 2 natural frequencies. 3 degrees of freedom system would have 3 natural frequencies. So this is actually the mathematical model by which we could find out the fundamental frequency of the system. In order to find out, or in order to derive the equation of motion for the modeling of the system, vibrating system, we would be using a number of methods. One of the methods is the Newton's method or Newton's law. In Newton method, we would be using the Newton's second law of motion, which is F is equal to mass into acceleration. But we would slightly actually modify that equation. We would write down that as summation of all of the forces which are acting along the displacement of the system, or which are responsible for the, or which are along the displacement of the system, must be equal to mass into acceleration. X double dot is acceleration. So this is the Newton's second law of motion for the linear system, or translatory system. and this is the Newton's second law of motion for the solar system. Summation of all of the moment about the axis of rotation must be equal to mass mode of inertia I naught about that axis times angular acceleration. Theta double dot is the angular acceleration. So in order to find out the equation of motion, one of the methods that we could use is the Newton method, which is based on the Newton second law, uh, second law of motion. This is the lump parameter model, simplest model that could be possible for a vibratory system. Mass, we are taking all of the mass at one, and all of the stiffness or elasticity, which is actually distributed, we are taking in this thing, having stiffness scale. And x is, let's say x is the displacement of the system. And here we could see a toroidal system. It's comprised of a rod, one end rod of one end of the rod is fixed, whereas the other end of the rod is connected to this, and this when it is displaced, it is vibrating about the system. So further on learning, let's say we have a spring mass system, and the mass is vibrating. We have, let's say I'm pulling this mass up to here, and then I have released the mass, and then the mass is vibrating about the mean position, and it is vibrating at its own. It is vibrating in the absence of the disturbance force, external force, and such type of vibration is free or natural vibration. So we have a natural vibration. The system is under natural vibration. Next, what I would do, I would draw the figure diagram for this. So we have this mass. Let's say at this distance, the mass is moving in the downward direction. It's moving in the downward direction. So if the mass is moving in the downward direction, so what would happen to the spring? The spring would stretch. And what would be its effect? It would pull the mass in the upward direction. So if I draw the figure diagram of the system, so we would have this mass. So this is the mass, and it is moving in the downward direction. It has displacement x, and the spring force is acting in the upward direction. If the mass is moving in the downward direction, the spring force would be in the upward direction. It would be pulling the mass. And the spring force is K, as we discussed before. K is the stiffness. It is F by X from there. So the spring force F is equal to K, which is in the direction. So this is the free body diagram of the system. Applying the Newton's law on that, that is summation of all of the forces which are acting on the system or acting on the mass must be equal to mass times acceleration. So we are writing that as mass times acceleration, which is equal to summation of all of the forces which are acting on the mass. All those forces which are along the displacement, we have to take those positives. And all of the forces which are opposite to the displacement at that instant, we have to take that negative. So here only we have one force, and it is opposite to the displacement at that instant, so we have to take that negative. So minus Kx. And now bringing this term on the other side of the equation, we would have mass times acceleration mx double dot plus kx is equal to 0. So this is actually the equation of motion of the system. This is representing the dynamics of the system. Now this is representing the vibration of the system. Kx is the spring force, where mx double dot is the inertia force. It is the inertia force. And if you look here, that the direction of inertia force is also in this direction. This is positive here, this is positive here. So if this is positive, it is in that direction, so it must be in that direction. And like in direction. Inertia is always actually resisting the motion. So if the body is in that direction, so the inertia force will be in that direction. So mx double dot plus kx is equal to 0. This is differential equation. This is the differential equation. And you could see two rods, second order differential equation. It is the second order differential equation. And you could see a 0 here. So this is homogeneous differential equation. If we have some quantity here, and that quantity was a function of time, then it could be actually non-homogeneous differential equation. So we have a differential equation, second order differential equation, non-homogeneous differential equation. These are constant, n is constant, k is constant. So the coefficients are constant, and also you could see that the power here is 1, and also the power is here is 1. So this is a linear differential equation. So we have a linear second order homogeneous differential equation, and that differential equation represents the motion of this system. So we call this as a governing equation or equation of motion of this fabric. And for this system, the system is vibrating, so it would have frequency. Frequency is the number of the frequency is actually number of cycles per second. So, and we have already modeled this as the circular electric frequency megaamps. So this vibrating will be K bar in the video. Similarly, if we have a coordinate system, if we have a rod, one end of the rod is fixed, whereas the other end of the rod is connected to a disc. And if I apply a moment on this disc, displace it to some angle, and then I release the disc, what would happen? This would start vibrating about the axis of the rod. It would start vibrating about the axis of the rod. Again, this would be free vibration. It would vibrate at its own in the absence of the disturbance or external force. So it would be the case of free vibration. And normally we call this a torsion system. And in this case, the Newton's law would be summation of all of the torques that are acting on the system must be equal to the mass moment of inertia times the angular acceleration. So mass moment of inertia of the disk about this axis of rotation, let's say it is I, and theta double dot is the acceleration of this disk during the vibration. It must be equal to summation of all of the torques in the system. We have this rod, and it would have the rod is elastic. It would have stiffness, and it is under torsional vibration. So we turn the stiffness in such type of vibration as torsional stiffness. And here, The torsional stiffness is denoted by K subscript P, and it is defined as the torque which is required to produce unit angular deformation in a material. The torque which is required to produce unit angular deformation in the material. So here, by this equation, this torque would be equal to K subscript T torsional stiffness times the angular deformation or displacement theta. Angular displacement theta. So this is the torque, restoring torque. This is the restoring torque of this rod. This is the torque which is produced in this rod because of this theta. So if you displace this to a angular displacement theta, then the restoring torque that would be produced it would be Kt theta. So here, if the displacement is in that direction, the restoring torque would be always opposite to that. So here, T, which is the restoring torque, which is the torque due to the stiffness of this rod, it would be in the opposite direction. The motion is in that direction, the restoring torque is in the opposite direction. And all those torques which would be along the displacement, you have to take those positive. All those torques which is opposite to the angular displacement, we have to take them negative. There is only one torque, and so that torque is opposite to negative, and it is actually Kt theta, so Kt theta. And bringing that term on the other side of the equation, then we have I theta double dot plus Kt theta is equal to 0. So this is the governing equation for the torsional vibration, single degree of freedom, torsional vibration, torsional system. Or this is the equation of motion for that system. And the circular natural frequency for this system is actually omega n. It is equal to Kt. Kt is the torsional stiffness when it's divided by I, the mass moment of inertia. So this is the mathematical model for the natural frequency, undamped natural frequency for this system. The other method that we could use to determine the equation of motion of the system is the energy method. Now, since there is no damping in the system is conserved, we could use the law of conservation of energy, which is actually that energy can neither be created nor distributed. The total energy of the system would be always constant during the vibration if the vibration is undamped vibration. If there is no losses in vibration. Let's say we have a spin mass system, there is no damping, so you are not seeing the damper. So if we have a spin mass system, if it is vibrating, it is moving, then the system would have energy. It would have kinetic energy, and it would have potential energy. When the system is vibrating, so it would have these two energies. At the mean position, let's say this is the mean position of the system. Mean position or equilibrium position. And during vibration, if the mass would be moving in the downward direction, it would be the extreme position. So let's say this is one extreme position. Extreme position. It would reach the extreme position, it would stop here, and then it would start moving in the again towards the mean position. It would pass to the mean position, and it would reach the other extreme position. Extreme position. And again from there it would stop, and then again as the spring would have compressed, would push the mass, and the mass would be moving towards the mean position. It would reach mean position, and then it would again move towards the other extreme position. So this way the system would be passing through the mean position, reaching the down extreme position, and from there again it would be moving towards the mean position, and then it would be the extreme position. Here, when it is reaches here and it stops, what would be its velocity? Its velocity would be zero here. So what would be its kinetic energy? Kinetic energy would be zero at the extreme position. But as it would start moving back towards the mean position, its velocity would increase. Its kinetic energy would increase. And as it reaches here, it would have maximum velocity. It would have maximum kinetic energy. Kinetic energy is actually half m squared. If the velocity is maximum, so it would have high kinetic energy here. And as it would further move towards the other extreme position, its velocity would slowly and gradually decrease. And when it reaches the other extreme position, again when it stops here, its velocity would be zero. And when its velocity would become zero, so its kinetic energy would become zero. When it reaches here, the spring would be completely compressed. The energy, the kinetic energy which the system has, it would be stored in this spring in the form of potential energy. Potential energy. And actually that is called, here it would be the strain energy. It would be the potential energy. Here the potential energy is actually the strain energy. Okay. Here the strain energy, which is stored in the spring because of deformation. And energy. It is stored in the spring because of deformation. Energy. SE. And here we would study this later on. This strain energy in this spring is of k x squared. X is the deformation in the spring. And kinetic energy is of mv squared. The kinetic energy is maximum at the mean position. It is half mv squared, which is here the kinetic energy is how much? It is half m x bar. So the kinetic energy is maximum at the mean position, whereas it is zero at the extreme position. The potential energy, here it is in the form of strain energy, it is maximum at the extreme position. At this extreme position, the potential energy of strain energy is maximum, and also at this extreme position, the potential energy of strain energy is maximum. These are the intermediate. In between these extreme position and mean position, we have intermediate states where the system would have both potential energy and kinetic energy. But when the system reaches here, the displacement would become zero. So the potential energy would become zero. So at the mean position, the potential energy or strain energy would be zero, because at this point, at this position, the spring would be neither stretched or expanded. So it would have zero force. So it would have zero strain. X would be zero here. If you put X is equal to zero here, the potential energy would be zero. Remember that in the extreme position, kinetic energy is zero and potential energy is zero. Whereas at the mean position, the kinetic energy would be maximum and potential energy, that is strain energy, would be zero. And in the all intermediate position between these two positions, we would have both. So when the system is vibrating, so the system would have potential energy, it would have kinetic energy, the kinetic energy would be converting into potential energy, and then the potential energy would be changing into kinetic energy. And this would be actually reflecting using your position. Here we have two energies. So generally writing for the intermediate position, let's say intermediate position I. Intermediate position I. What is the total energy at this intermediate position? Potential energy plus kinetic energy, and it must be equal to constant. The total energy of the system will be always constant. Energy can neither be created nor destroyed. So P plus Ke must be equal to constant. Let's say U is the potential energy and capital T is the kinetic energy, so it could be equal to constant. And if we take derivative of this equation on both sides, so we would have d by dt U plus P is equal to 0. The derivative of constant is always 0. So the energy method, according to energy method, we come up with this equation d by dt U plus P must always equal to 0. So now let's use the energy method to determine the equation of motion of the system. So potential energy, it is stored in the spring as strain energy, and this energy is actually equal to half kx squared, where k is the spring constant or stiffness of the spring and x is the displacement that is actually happening in the spring because of vibration. And kinetic energy is equal to half mx dot square. So, and this is the equation for the energy method. d by dt U plus P is equal to 0. Potential energy plus kinetic energy. So putting these terms, half kx squared plus half mx dot squared is equal to 0. Next, we have to derivate these two terms. So this is constant, and we have to differentiate this. So 2 would come, and that 2 would cancel with this 2, and then we would have x, and then we have to differentiate x to x2 plus 1 by 2, and this 2 would come from there, and it's constant. This 2 would come from there, so that 2 and this 2 would cancel, and we would have m and x dot, and then x double dot, and it must be equal to 0. Now, if you look here, x dot is actually common here. So x dot times kx plus mx double dot is equal to 0. Now, again, this is a mathematical equation which is actually saying that either x is equal to 0 or the quantity inside the bracket is equal to 0 at all times during the vibration. So either this quantity is 0 or this is equal to 0 or both are equal to 0. But if you look here, x dot is velocity. It is the velocity. And we know that when the system is vibrating, the velocities are zero only at the extreme position. In all other positions, intermediate positions and mean positions, the velocity have value. So during all of the vibration from 0 to infinity, this quantity velocity is not equal to 0. What does that mean? In order to have this statement correct, it means that the quantity which is inside the parenthesis, it must be equal to 0 at all times during the vibration. And so it means that m double dot plus k x to infinity. And this mathematical equation represents the system at all times from 0 to infinity. This mathematical equation actually represents the system during all of the vibrations. We call this equation of motion, or the governing equation, which is representing the vibration. So again, using the energy method, we call the same equation. Similarly, finding the equation of motion for the torsional system, the potential energy would be stored in the rod in the form of the strain energy. The potential energy would be strain energy, and that strain energy would be half kT, which is the torsional stiffness, times the square of the displacement. And kinetic energy is equal to half I. I is the mass moment of inertia of the disk about the axis of rotation times the square of the velocity, angular velocity, theta dot square. So this is the mathematical equation for the strain energy, and this is the mathematical equation for the kinetic energy. Again, here during vibration, the kinetic energy is changed into potential energy, and potential energy is changed into the kinetic energy. There is no damping, so the energy would be conserved, and we could use the energy method to determine the equation of motion. So this is the equation for the energy method, E by dt, U plus P, U is potential energy, plus this here, and P is kinetic energy plus this here. After putting that, we got that equation. Again, differentiating with respect to time, we would get kt theta times theta dot plus I, theta double dot is equal to 0. Theta dot is common, when taking this common, theta dot is what? Theta dot is the velocity at which this is vibrating or moving. So this mathematical equation tells us that either theta is equal to 0, or this quantity is equal to 0, or both are equal to 0 at all instances during the vibration. And we know that theta, the velocity is 0 only at the extreme position, and all other intermediate positions and mean positions it would have value. So using the physics, the reality of the system, it means that theta dot cannot be equal to 0 at all times during the vibration. What does that mean? It means that the values which are inside the parenthesis, they are actually equal to 0. So I theta double dot plus kt theta is equal to 0. So again, we get the same equation of motion for the system.